Okay, let's get started. I'm Max McMullen. I'm the development lead for Direct30 at Microsoft. My team designs and implements the Direct30 API that I'm here to talk about today. So let's get started. First of all, please submit feedback at the end of the talk. It really helps us, keep on iterating on the developer content and give you what you want most in terms of value out of these conferences. So watch at the end for that. So the agenda. I really want to cover 3 topics today. First, I want to give you all just an update on where we stand with the DirectX12 family of technologies in terms of API, where we're at, driver state, and then the tools and other pieces of the overall ecosystem in terms of delivering Direct3012. The next 2 parts are actually interleaved. I have 2 developer experiences that I want to show you. These are AAA studios building technology demos or actual real games that are going to ship on Direct3012. And they're going to talk about their experience, or I'll be relaying their experience through notes to you. Third, the last remaining feature that I really haven't talked about yet in Direct3012 is multi-adapter support. So we actually have multiple levels of implicit and explicit support for enabling multiple GPUs on a given machine to interact and render cooperatively. And this is all in the general theme of Direct3012, giving you, the developers, more control and more power on these machines that are out there today, and realize your goals for whatever application you build, whether it's game engines or high-end workstation applications. So first, let's talk about the Direct3012 update. So it's been a pretty busy year. We first announced at GDC last year, early March. And throughout the year, there have been a series of talks where I've released more and more details about the API. Where we stand today is the API is largely complete. The SDK that you'll get that matches these builds recently flighted as part of build represents basically the final API. There might be a flag or 2 we have to add to the API surface over the next few weeks just to resolve the last remaining driver and hardware issues. But in general, in terms of worrying about whether the API is going to change on you, it's pretty much final. This is the time, if you want to be an early adopter but you couldn't deal with the API churn of the early access program, to start looking at the API and figure out how to adopt it for your engines. In terms of hardware support, we have working drivers across the 3 major PC GPU vendors. So AMD, Intel, and NVIDIA all have working drivers with good to leading edge performance. For hardware, based on the February Steam survey, actually 50% of gamers today on the Steam survey already have DirectX12 capable hardware. That's based on looking at the Steam survey results across the hardware IDs and also comparing against the pieces of hardware that hardware vendors have told us they'll support for Direct3012. Further, if we extrapolate over time, just looking at how the hardware has changed from month to month in the Steam survey, right now we're predicting about 2/3 of gamers will have DirectX12 capable hardware by holiday this year and continuing to grow to cover the large percent of gamers in 2016. Now, you might be thinking, well, I've heard DirectX12 is a Windows 10 exclusive. And when we first announced a year ago, we couldn't really talk about our distribution plans for Direct3012 and Windows 10. But now it's been announced that anyone running Windows 7 and later for an operating system will get a free upgrade to Windows 10. So really, Direct3012 is available to, by and large, that entire set of hardware out there. Everyone can do a free upgrade and get Direct3012. So you have a huge number of customers you can target with Direct3012 even this holiday alone. Along with the API development, we have actually had a team working in parallel to deliver cutting-edge tools for you to develop your games on Direct3012. Visual Studio Graphics Diagnostics now supports Direct3012, and it's fully capable of doing both debugging features and performance analysis. On the debugging side, it's capable of doing shader debugging. It's able to do analysis of rendering calls. You can look and find the few rendering calls that might be causing glitches in your rendering. On the performance side, you can analyze and look at CPU performance. You can look at GPU performance and find where the real bottlenecks are and optimize them down to be smaller overhead. The best part about this is it's also available free. The graphics diagnostics are in the Visual Studio Community Edition, which you may have heard about already at the conference. So Visual Studio Community Edition, I'll have a link at the end of the talk if you haven't seen it yet, but you can just download it and start playing with the graphics diagnostics. The second part that hasn't really been talked about too much is both the graphics tools in Visual Studio and the D30 SDK layers that we've shipped in 10, 11, and now 12. We've improved how they're delivered to you. So in the past, you had to do sort of hand matching. You had to install the version of the SDK that matched the operating system you were developing on. And in the past, you might have seen errors when you use the SDK layers. It'd pop up a message saying your SDK layers don't match the machine. Well, now the SDK layers in D3D and the tools are actually part of Windows Update. So once you install the developer tools and get the SDK layers on your machine, we're able to keep pushing new updates to the SDK layers to your developer machine. If you upgrade the operating system, you'll get a new SDK layers that matches that operating system. The other way we intend to use this is those SDK layers, we'll keep on modifying and updating them over time, and we'll take feedback from the community both in our early access program for DirectX and out in the other public forums for developers. We'll be watching and looking for the problems you run into most, and we'll figure out ways to put those diagnostics into the SDK layers and the tools. So it's really a much easier way to interact with Direct3D and the developer tools we have available today. Third part of this, DirectX12 adoption. So DirectX12 is actually already supported on a number of major game engines from Unreal 4, Unity 5, and several custom in-house game engines built by AAA studios and also indie studios as well. So our early access program has given developers the chance to get up to speed with the new API early and get that support out there. But if you haven't been part of that, then the public SDK is now ready for you to adopt. That said, early access will continue to exist. There's a link at the end of the talk. There's a great community there of people that have already been working through the API and working through issues they had in porting. So it's still worthwhile to apply if you have interesting applications under development. We'll get you into the program. Second, this has been the fastest adoption of a Direct3D API we've seen since Direct3D 9. It might actually turn out to be faster, but we have a few more numbers to crunch before we can say that. But suffice to say, it's been the fastest adopted API in more than a decade. There are a number of titles being developed both by Microsoft game studios and third-party studios from around the world. The two developer experiences I'm going to talk about today are actually from game studios from other parts of the world, not just the US. And so it's really great to be able to show you the wide variety of content and different types of games being built on Direct3D12. So that was the update. That's where we stand with Direct3D. The API is complete. It's really a good time to start looking at it. Let me move on to the first developer experience I have to talk about. So this is from Snail Games in China. Snail Games is one of the top developers in China. They're a great AAA studio. They have a huge amount of R&D being invested in developing new content. They're a diverse company. They work in a wide variety of media, mobile, desktop, console, also in other forms of media in terms of movies, et cetera. They have a large number of products targeting gamers and other types of products. This is the first game I'm about to announce from China to adopt Direct3D12. Their game King of Wushu has been released on Xbox recently, but they're actually porting to Direct3D12, and this will be the first game coming on Direct3D12 from China. So they've been porting in the last 6 weeks. We've been working with them. They're currently 10% higher in FPS already than Direct3D11, and that's just a quick 6-week port. There's a lot of perf they still have to grab, and we expect them to get much higher FPS over the months as they finalize their plans to port to Direct3D12. So again, if this is really great, it's a game coming from China, moving to Windows 10 and DirectX12 this year. So what I can show you is Snail Games has been really awesome. They put together a video comparing their engine, Direct3D11 versus Direct3D12. And so what you'll see in this video, actually, a number of times they'll show you 11 and then show you 12. In the upper right-hand corner of the video, you can see the frame per second counter. Below that, you can see CPU utilization and GPU utilization. The two key things to look at is you'll see much more consistent frame rate on 12. The second part you'll see is the GPU utilization is 10% higher consistently. They've taken that performance and they've been able to apply it to actual gameplay. So there are parts in the scene where you'll actually see more enemies on screen with Direct3D12 than Direct3D11. It's a great example of Direct3D12's power and control being used to create richer, better content. It's exactly what we were hoping for when we started Direct3D12 2 years ago. Let's start the video here. actually able to get 1.5 times the number of enemies with greater performance. You can see again there on the GPU utilization, there's 10% higher utilization on the DirectX12 path. This is just a 6-week port with 2 engineers. So that was great. Thanks to Snail Games for putting that together for us. So Snail Games couldn't be here with us today, but I want to summarize some of the notes they gave us in terms of DirectX12 adoption. It's for a 6-week effort. Usually, a lot of these engines and games, they have a platform-specific portion that's low level, and they have a higher level platform-agnostic part of their code. They have purely taken the lower levels, the parts that are platform-specific, and ported them from DirectX11 to DirectX12. So given that, they've adopted a number of the core technologies in DirectX12, from parallel command list generation on multiple CPU threads, utilizing the lower per-core CPU overhead that DirectX12 has to offer. They can submit commands on multiple queues at once. They're using multiple engines, so they can stream with a copy engine on the GPU at the same time that they're rendering the current frame. So it's reducing glitches from having this parallel streaming optimization. Next, memory efficiency. I talked to GDC about how to allocate resources on DirectX12 and the new features we have, giving you greater control. So they allocate large chunks of memory on a separate thread from rendering. They can partition that and reuse the memory efficiently, avoiding glitches. They get more efficient memory usage because they're no longer hanging on to resources for extra amounts of time. They can frame to frame decide how to allocate resources. Finally, with DirectX12, if you look at some of the earlier talks, I talk about how you've taken all this fine-grained state. So, in the pipeline, you have vertex shaders, geometry shaders, pixel shaders, blend state, rasterizer state. And in 11, you could individually set those. 12 combines them all together into a pipeline state object. Those can be compiled on a separate thread and created ahead of time. So when it comes time to actually issue draw calls and other rendering operations, there are no compile operations being done real time by the driver. So there's fewer glitches with all that compilation work moved to separate threads. Next, as I've mentioned a couple times already, DirectX12, because it provides us greater performance and greater control, it really allows you, the developer, to realize your vision for whatever graphical application you have, whether it's a game or a workstation app. In this case, they've taken the greater performance of DirectX12 and put those increased number of enemies on screen. I imagine that as the months go on and they get more and more perf, they'll figure out how to keep their, fully realize their creative vision for the game using that increased perf. Last, actually, because they had an Xbox One port already, Snail Games was able to leverage that effort in porting to DirectX12. One of the original goals we had for DirectX was to be multi-platform across Microsoft, so phone, PC, and Xbox One. And Snail has realized that a lot of their effort building the Xbox One version with 11x and 12 is now leveraged by the 12 path and the API. The APIs are largely converged, so Xbox One and PC, 12 is pretty much the same. So it's really easy to make code work on both platforms. Okay, so let me transition. I'm going to start talking about multi-adapter a little bit, and then I'll talk about the next developer experience, and I'll finish up with multi-adapter and a tech demo about multi-adapter. So there are multiple layers of multi-adapter implementation in DirectX12, really allowing you to scale how much effort you want to put into supporting multiple GPUs. The first level of multi-adapter implementation is implicit multi-adapter. This is what we've been engineering in DirectX12 for a while now, and it's basically the same experience and guidance as DirectX11. So if you don't really want to deal with a lot of multi-adapter issues on your own, It's possible as long as some care is taken to avoid things like cross-frame dependencies and use enough swap chain buffers that the driver can implement multi-adapter for you. The best performance is usually achieved by working with hardware vendors to optimize, but this is a great step into the multi-adapter feature. One enhancement that Windows 10 has is that we've actually made it easier for hardware vendors to implement implicit multi-adapter in windowed mode swap chains. So if you have an application that's really high-end rendering, it can leverage multiple GPUs, but you don't want to do fully explicit multi-adapter, now you can, the hardware drivers can more efficiently take advantage of the two GPUs even in windowed mode. So this is what we had rendering. This is what we had working for multi-adapter when we first started the next developer experience working with Square Enix. So Square Enix, you all know, I'm sure, a studio with a long, long history building incredible games with cinematic experiences. And they've worked with us in NVIDIA to build the art and tech demo called Witch. You saw this morning in the keynote. That was rendering live on quad SLI with implicit multi-GPU. It was rendering at 4K and then scaled down to 1080p. So I'm going to show you a video. This video is recorded from one of the practice sessions for the keynote. I'll talk through what the user was doing when they were driving this live and explain a little bit of what's going on. Okay, so it's going to play through again. I'll try to keep up with the video. So what you're going to see is the same demo start, and then the user is going to flip into manual control. So here we're in manual, just changing the camera viewpoint, looking through a real-time rendered scene on this quad SLI. Zooming in and out, great atmosphere. This is incredibly realistic, high-end rendering. You can see the time of day changing, the shadows moving across the landscape. Here we can show the really detailed character animation. This is truly, truly cutting-edge bleeding rendering on DirectX12, running on quad SLI. Detail in the feathers and the animation on the character is incredible. Here again, you can see the time of day shifting and the level of detail, just even on these fine pieces of art in the landscape with the shadows moving. And back to the character, you can look at the detail on the clothing, all the animation and the physics simulation involved in making the character move realistically. Next, the detail in the skin. These are incredibly high-resolution textures. And making skin look like this requires multiple levels of shader and lots of layers of lighting. This is all, again, running on DirectX12 with multiple GPUs rendering at 4K. And finally, the hair. One of my favorite parts. This is incredibly realistic hair. That's actually geometry being rendered with an isotropic shading. So, brief switchback. So we asked Square to provide some feedback and experience to you all on their experience. And they filmed their developer, Ivan Gavrenkov, talking about his experience with DirectX12. Ivan's actually here in the audience, and so I just want to take a chance just to thank Square and Ivan for putting together such a remarkable demonstration of technology. This is truly bleeding edge graphics on a brand new API with a lot of features. So thank you, Ivan and Square, for all the effort you put in.
So, Ivan, is Square Enix happy with the greater control they have over the GPU now?
Yeah, so talking about D3D12, the first thing I want to mention is that with D3D12, developers are getting greater control over the GPU. One of the biggest changes is in how you bind the resources, textures, and buffers to the shader stages. With D3D12, developers are free to manage the limited space that's available for resource binding. So we can choose to use tables, and that allows us to bind more resources, or we can use the single resources and inline constants, which are cheaper. For example, it's possible to bind all the resources that were in D3D11 spec, so 128 textures and 16 buffers. But if you do that, you'll probably have to cache and manage all that state, and that might be quite heavy on the CPU. So I like that we get to choose if we want to have more resources, but then we'll have to spend a little bit more CPU time managing that, or we want to have the raw power, and then we can bind less resources to the shaders.
So you have a choice between whether to allow the driver to manage or to manage yourself.
Yes, so when talking about memory management in D3D12, it allows us to directly manage the GPU memory. So the way it works, we allocate the large heaps, and then we sub-allocate resources into those heaps. So now developers are able to detect the out-of-memory conditions and then react to that accordingly. So for example, if we detect that, we can move some of the resources back to the main memory, or we can decide to defragment that heap. At the same time, there is still a way to let the driver to manage the memory for you. So you can choose if you want to manage the memory yourself for some heaps, and for the others you can let the driver to do the work for you.
So what will Square Enix be able to do with DX12 that you think customers will appreciate the most?
So one important change in D3D12 is a lower cost of the draw call. So we are also allowed to create commands on the GPU, several threads at the same time. So I think if developers can leverage this properly, it's possible to provide a better experience for the players that they can appreciate. For example, we might have more moving, unique looking objects, or we can have more shadow casting lights, or we can have larger draw distance.
So the lower cost of a draw call will potentially give you a much greater increase in your draw call count, will it not?
Yes, right. So I think increased draw call count is quite important. With GPUs becoming faster and faster every year, I think the graphics APIs haven't evolved so fast over the past few years. So with D3D12, I think that's going to change, and we can finally utilize the modern GPUs to the fullest.
So how long did it take Square Enix to port to DX12? Did you run into many problems, or was it rather straightforward?
So I think it took around 3 weeks to get the basic rendering working. And comparing this to my previous experiences of implementing a new graphics API layer, I would say it was quite straightforward. However, I have to mention that this was a direct port, and it wasn't using many of the unique features of D3D12. Going forward, I think we're going to adjust some of our systems in the engine to better match D3D12. So personally, I think it's not very difficult. It wasn't very difficult for us to try the D3D12, but with any new platform and any new graphics API, you probably know that you need some time before you can utilize the API for the 100%.
Great, thank you for your time.
Okay?
Okay.
Thanks, Ivan, and swearing next again. That was just the developer experience. Okay, so moving on, let me finish up with explaining the rest of explicit multi-adapter and show you another demo based off of explicit multi-adapter. So beyond implicit multi-adapter, which was already available in D3.11, 12 goes one step further, again, along the theme of giving you the developer more control. You actually have the ability to target multiple GPUs, and it builds on concepts already designed into the 12 API. So 12, as I talked about back at GDC, has multi-engine support. You can issue commands to 3D, to compute, and to copy all on independent queues. Well, now that just extends to where you can actually use multiple threads to target 2 different GPUs on all those different engines in parallel if you so choose. Next, in terms of memory allocation, again, independent memory allocation and management across multiple GPUs. You can create resources on one GPU, create resources on another GPU, 2 different threads. And then you can also create new special resources that are shared memory that you can write to and read from with both GPUs. Last, to coordinate all this effort across those parallel queues, the synchronization objects in D3.12 can also be shared across adapters. So work on one GPU can then signal a fence that causes another GPU to continue processing commands. We'll actually use this capability in a demo later to do a single frame of rendering on 2 GPUs simultaneously. We'll render part of the frame on a discrete GPU. That discrete GPU will signal a fence that then causes the integrated GPU to finish rendering the frame. Beyond integrated and discrete combinations, which just haven't been possible in D3 before, this also is, this feature exposes explicit control of 2 linked GPUs as well. So what you might know as Crossfire SLI from AMD and NVIDIA respectively, you'll get direct control over both GPUs in Direct3.12 if you so choose. Next, because you have this explicit control, really it's possible to do whatever type of custom load balancing you can imagine. I'm going to show you that tech demo I mentioned, which is collaborative rendering on a single frame. But really, all sorts of designs are possible in your engines. You could be doing simulation on the integrated GPU. You could be doing the warp for a VR headset on the integrated GPU. In parallel, you can be doing like the big 3D scene rendering on a discrete GPU. Likewise, you can do your own custom split frame rendering or AFR yourself if you want. So I've mentioned 2 cases. There's linked GPUs and unlinked GPUs. Again, linked GPUs is traditional Crossfire SLI. Unlinked GPUs would be 2 distinct GPUs, potentially from different vendors, like having an Intel integrated part and an NVIDIA or AMD discrete part. So let me first talk about linked GPUs. I'm not going to delve into this too much right now, just because linked is actually the richer, more complicated scenario. I'll have a talk dedicated to this where I'll talk in detail about linked. I want to focus on the unlinked part, which is the demo, and that'll create some building blocks later to talk about linked. But just at a high level, linked GPUs in Direct3.12 look like a single GPU, but you have the ability to create queues like 3D queues and copy queues targeting each individual processor. Likewise, when you allocate resources, you can actually specify which GPU those resources are local to. So you can optimize for whatever given rendering you want. If GPU A is doing some heavy lifting on one resource, you'd allocate that resource local to GPU A. But eventually, when you want to move that resource to GPU B, B can access it across whatever dedicated bus, whether it's a specific hardware bridge that's been added across the cards, or whether it's over PCI Express. So again, API, linked GPUs, it looks like a single GPU, but we enumerate more and more engines that are possible to target. And it's a much more seamless experience with resources. But let's move on to the more general case. This is really interesting in terms of unlinked GPUs. These are 2 completely unrelated GPUs. Again, it could be Intel integrated, NVIDIA discrete. It could be AMD discrete and Intel integrated, or AMD integrated as well. The fundamental primitives here is we've created a way in D3.12 to allocate memory that is accessible by both GPUs. and an ability to synchronize rendering work across the different queues. One queue can be on one GPU, and another queue can be on the second GPU. So these two primitives, having shared memory and shared synchronization primitives, allows you to build whatever type of collaborative rendering workload you want to create. So at a high level, we have explicit multi-adapter resource management. You can create and manage resources on two GPUs simultaneously on multiple threads. What we've added, if you imagine GPU A is integrated and GPU B is discrete, the discrete GPU can say, take a view of a resource that's allocated on the integrated GPU. And so what you see there is GPU virtual addresses from both GPUs mapping to the same pages that are in system memory local to the integrated GPU and GPU A. Likewise, building on the fundamentals, so Direct12 has these independent queues, and you can just target multiple GPUs simultaneously. What I'm showing in this scene is just two GPUs doing similar rendering workloads and synchronizing only in GPU local synchronization primitives. But what we can do is we can look at more complicated scenarios now where we're synchronizing work across multiple GPUs. Again, if you imagine that GPU B is a discrete GPU and GPU A is an integrated GPU, it's possible to split a given frame of rendering. And so you actually have a flow of data moving from processing on the discrete GPU to a copy engine which moves the data to the integrated GPU. Then the integrated GPU processes commands. So you can see a given frame might progress in time and be pipelined through these synchronization primitives. Briefly, just to point out, these octagons, red octagons represent weights, and the green circles represent signals on synchronization primitives. What you can see is GPU B is actually signaling a fence that is shared with GPU A. So A is waiting on this signal to occur. And that's why the frame progresses. So 3D rendered back here. Then there's a copy queue copying that frame to the integrated shared memory. This GPU waits for that copy to complete and then processes the end result of the frame and presents it. And so you can imagine over time, there are multiple frames pipelined, and they'll progress through the system in this way. So let me make things a little more concrete by talking about the tech demo. That was a high-level look. Let's go one step deeper in terms of multi-adapter on this tech demo. What the Direct30 team did is we took the Unreal Engine 4 source code, the Direct3012 port of it, and we coded a special path in it to do multi-adapter cooperative rendering on integrated and discrete GPUs. And so whenever you do this cooperative rendering on a given frame, you have to decide how to divide the workload for the frame. What we decided to do is separate the post-processing step. So we look at, after the 3D scene is rendered, there's usually a series of post-processing steps to generate the final frame. We split that post-processing step and put part of the workload on the integrated GPU. So the discrete is doing the bulk of the 3D frame, and then integrated doing post-processing. So why did we pick post-processing to put onto the integrated GPU? It's easily pipelined, so it's easy to sever a point. It's contiguous, so we aren't going to have to move data back and forth multiple times per frame between integrated and discrete. Next, predictable workload. When you think of 3D scenes, there's lots of stuff going on. There are characters appearing, disappearing. You'll be streaming lots of resources in the background. You never quite know where the user is going to look. So that's fairly unpredictable, and a lot of games spend a significant amount of engine effort trying to predict what workload is going to appear. It makes things a little complicated trying to deal with two different workloads that are simultaneously varying a lot. So post-processing is nice in that it's fairly consistent from one frame to the next, and that's what we put onto the integrated GPU. So the other benefit is it has clear dependencies. Post-processing usually involves taking a frame, taking that input, running some processing on it, writing the output, taking that output, doing the next pass on it. It's not like you're pulling in lots of textures or geometry into the post-processing pipeline, so it's really easy to manage the number of resources involved. That same benefit, that small number of resources makes it predictable, so we know exactly how much we're copying in at one point in time. So if you look at a post-processing data flow, this is just a high level. You can see there are a number of steps. Now, the GPU actually doesn't do all these in discrete steps. Usually, a lot of them can be optimized together. But in general, what you see is the rendered 3D scene starts at the top and flows through the processing steps and results in a final frame at the very bottom. And what we're going to do to implement multi-GPU is we're going to cleave this post-processing data flow at some point where the integrated GPU can keep up. And the way we did this in Unreal Engine 4 is we put in a new copy node. That copy node will take the resources needed on the discrete GPU and copy them into shared memory, coordinating with those cross-GPU synchronization objects. Overall, it's a simple concept, but the trick is in picking where to cut across the post-processing pipeline. The general theme of what we tried to do is we picked a point in time where it was guaranteed the integrated workload is always equal to or less than the discrete workload. That way, the discrete GPU is always, moderating the final frame rate. What it looks like in a frame timing diagram of synchronization is this, where you can see, look at frame 1, you'll see the 3D NVIDIA rendering in the demo taking the bulk of time. There's a synchronization primitive to move from the 3D engine to the copy engine on the discrete GPU. That copy is a relatively quick step. And then there's a cross-GPU synchronization primitive to synchronize between the copy queue, which was copying into a shared memory. And the integrated GPU wakes up and finishes the post-processing steps and finally presents the frame. So on the timeline, what you see is the overall time of execution is gated by the discrete GPU in this design. But what we've done is we've taken some of the workload off of the discrete GPU, so overall there's less time being spent in the system. In terms of pseudocode, it'll look like this. You can see some rendering commands on the discrete GPU with 3D draws, and then a signal indicating the rendering is complete. The copy engine, again, there's a wait for the rendering to complete, followed by a copy into a cross-GPU shared resource. Last, there is a synchronization primitive between the discrete GPU and the integrated GPU, indicating that the copy is complete, and the integrated GPU can pick up the remaining frame, complete the post-processing, and present. So let me show you a video of this running. What you're going to see in this video is a side-by-side comparison. So this demo is constructed as a race. We have 635 frames from the Elemental demo in Unreal Engine 4. So if you ever downloaded Unreal Engine 4, there's a bunch of content demos you can watch. So we have 635 frames. It has a fixed time step. So the GPUs all have the same workload. And the GPU configuration, whether it's just a single GPU or multiple GPUs, the one to get to the end of the 635 frames first is the one that's faster. So. There you have it. That's a multi-GPU configuration sharing rendering workloads for a given frame with the two GPUs actually exceeding the performance of the single discrete GPU alone. So just to show some timing, again, this is actual measured data. We just converted the GPU view diagrams into something that's easier to see on a large screen. So with the standalone discrete GPU, what you can see is it's approximately 28.2 milliseconds per frame. When we split the workload across multiple GPUs down below, what you can see is the discrete GPU still determines the overall frame rate, but part of the workload has been moved to the integrated GPU. So per frame, the actual pipelined cost is 25.3 milliseconds per frame. It's a little over a 10% win given this configuration. This is a highly unbalanced config. There's a relatively lightweight integrated and a relatively fast discrete. Different combinations will be possible, depending on whether you have a hybrid laptop, say, that has two GPUs in it, or a desktop machine. So 1 second, let me just advance this. Okay, so overall, that's multi-adapter. It's just a great new tool for you as developers to take advantage of. When you imagine new rendering workloads in the future, you could say, put simulation or other workloads on it. If you're managing, like say you had a shadow mapping pass or something else where you could actually parallelize the generation of the shadow maps, that can be moved to the integrated GPU. If you have AR, VR, you can do the warp on the integrated GPU as well. So to summarize, API is done. Multi-adapter is the last feature to announce for Direct3D12. We have tools available. It's all ready for you to start developing, and drivers across all the major hardware vendors. The 2 developer experiences I showed you today, plus many, many more under development. And last, multi-adapter is just a lot more power you have available in the system. And we're really looking forward to seeing what you can do with a multi-adapter feature in Direct3D12. Some resources. These are a list of all the talks that have been in Direct3D12 over the last year. They're all incremental. It's really hard to talk about the API just from scratch for every hour talk. But if I said some things that you might not be following, go back and watch these talks. And then second, here are some links to the tools I mentioned earlier in the talk. These are graphics tools for Visual Studio Community Edition. There's a blog, so any updates to the tools you can see on the blog. Second, those are the Direct3D12 links, so we have a blog tracking the progress in Direct3D12. The documentation is online. It's in a preliminary state right now. It's being updated, but that'll be rapidly iterated on as we get closer to ship. Last, early access. It's still relevant. If you want to get into the community of people that have been working on Direct3D12 for a while, it's a great way to get a head start in the API. Over the next couple months, we're going to be working on ways to get that community of early access more publicly available. So stay tuned on our blog, actually, for updates on how you can see more about different people building Direct3D12 applications. Last, samples. They're coming soon. Watch the blog for an update. That's it. Thank you. I'm available for questions here and then after, I think, in the Insiders Lounge. There's a microphone actually in the center.
So when I was looking at the graph of the demo, is there a concern that the total time to render the frame is bigger? So especially in VR applications, that latency and frame rate might be an issue. What are your thoughts?
Absolutely. So that's an artifact of how we chose to build the tech demo. We just wanted to find a simple way to prove out the overall technique. So we chose splitting a single frame that way. If you can actually find truly parallel workloads within the given frame, that's always better, and that can let you leverage the 2 GPUs without increasing latency. So it's really just a matter of ease of tech demo versus, once people have more time to look at Direct3D12 and think about their rendering stack in new ways, we expect it to be more and more parallel.
Look at it regarding energy consumptions. I guess if both CPUs work, you need more power, but maybe if you only have the desktop and then the discrete CPU shuts down, it may be an advantage.
Yeah, so actually there are a lot of power questions involved with this. In terms of truly portable form factors, there's just a power budget. There's only so much they can cool. I think there's still a lot for us to explore in terms of when it makes sense to split rendering workloads versus when it does not. But the first part in getting there is actually just giving you the control to use both of the GPUs. And then we'll see from there which workloads actually make sense to use too and which ones don't. There may be cases where you're better off using one GPU and not both. That get everything? Cool. If that's it, I'll be available in the Insiders Lounge afterwards. Actually, I think I'll be here for about 10, 15 minutes, and then I'll move to the Insiders Lounge if you have more questions for me. Thank you.